happen to stars when they die. This is what will happen to our sun when it dies. The outer layers are going to puff off into space. It'll run out of hydrogen. There'll be no more fuel left to keep the sun going. And the inner part of it's going to collapse, and it makes what's called a little white dwarf in here. So the core of the star collapses. There's no more nuclear reactions going on in there. It'll lose control of its outer layers, and it'll puff off into space, making a nice planetary nebula. The Earth will be around here, so that's curtains for us. And that's about 5 billion years time, luckily enough. The sun is about 5 billion years old. It's halfway through its lifetime. Of course, the sun's a bit bigger. This is what would happen to it. This is the Crab Nebula. So stars even bigger than the sun will have an even more dramatic ending. And this is the Crab Nebula, named by the Earl of Rossen from some of his observations made from Burr. So as well as the stars and the planets, we have stuff in between the stars. It's called the interstellar medium, and we like to study that because we want to see how the stars are made. These pictures here, they're in the Orion constellation for anybody who's into amateur astronomy. And we can now see planets forming from dusty disks around stars. But we want to learn a little bit about the interstellar medium, the gas and dust around those. And for the last few years, of course, we now know that there's not only our solar system, there's also planets around other stars called extrasolar planets or exoplanets. I think as of yesterday there was 1,912 planets discovered around other stars, so there's lots of them. And actually it seems that almost everywhere we look there's planets. So our lovely theory of the solar system doesn't appear to work very well anymore, because none of these look like our own solar system. So it's a huge area of research now. So after stars and planets, we have star clusters. So the stars aren't sprinkled uniformly around the universe. They tend to cluster because they form in these gas clouds. This is a picture here of the Pleiades. You can see that with the naked eye, and if you take a photograph, you'll see bits of wispy cloud around it. So that's just the leftover cloud from where the stars were born. They'll probably move off away from each other a bit later in their lives. And we also have larger clusters here, the globular cluster. Some of the oldest things in the universe are globular clusters, about 1 million stars grouped together. But even on larger scales, stars cluster together into what are called galaxies. So you might get this idea that there's structure, there's clusters, there's clumpiness or lumps all over the universe. This is a picture of our nearest neighbours called the Andromeda Galaxy. And this is what the Milky Way galaxy would look like if we were outside it. So all these individual stars that you can see here, they're just foreground stars. They're in our own galaxy. This is the Andromeda Galaxy here. Old, colder red stars in the middle and hot, young blue stars on the outside. These are satellite galaxies around it. Here's another lovely picture of the Whirlpool Galaxy, another one that was studied by the Earl of Ross in Burr. These are all stars and some gas and dust. They're the only place in the universe now that stars are being made anymore. The universe there's not enough stuff around anymore to make new stars, except in the spiral arms of these galaxies. Now, if we look at these galaxies not just with optical lights, this is what our eyes see, and our eyes are tuned to see things like our own sun. And these are stars like our own sun. But if we had radio eyes, so we could look at radio called electromagnetic radiation, same as light, just a bit lower energy. This is the kind of thing we might see, particularly when we look further away. This is what a galaxy looks like. This is called an active galaxy. And in the centre, you actually have a supermassive black hole, and you have matter falling into that. You have a magnetic field that gets wound and twisted up, and electrons shoot along that into the intergalactic medium, the stuff between the galaxies, and eventually it crashes into that and slows down and we get these hotspots. So that's what an active galaxy looks like. This is a picture of the radio signal, so it's using a radio telescope. These are the jets of electrons again coming out of the centre. This is an optical picture superimposed on it. This is what our eyes see. Right in the centre where the black hole is, you can actually see matter spiralling around it, about to fall in. So that's they're galaxies. But even the galaxies themselves aren't spread uniformly around the universe. They're clustered into clusters of galaxies. And the clusters themselves are clustered into clusters called superclusters. Our cluster, for anyone's interest, is called the local group. So if there's not many things in the cluster, it's called a group. And if there's lots of things in it, it's called a cluster. So we're in what's called the local group, and it's part of the Virgo supercluster. So that's where we are in the universe. If you look then at a larger scale, this is what the universe looks like. This is a slice through the universe. So we're at the centre and we're taking a slice in front of us and a slice behind us. And of course our galaxy gets in the way and blocks things. That's why we have these kind of big chunks taken out of the diagram here. Now in astronomy we kind of time travel because it takes light a certain length of time to travel. So the sun is 8 light minutes away, we see it as it was 8 minutes ago. We've no choice in that. The next nearest star is 4 light years away, so we see it as it was 4 years ago. We've no choice in that. So as we look further away, we're also looking further back in time. So really far away in the universe, things were hardly forming, so they're just sort of starting to form here. But if we can look at the universe now, on a large scale it's smooth. In other words, if I had a box over here on the left-hand side and a box over here on the right-hand side, the universe would look kind of the same in both boxes. It doesn't look dramatically different. But on all smaller scales, it's very lumpy. There's filaments and voids. And cosmologists have to explain that. They have to explain why the universe looks clumpy like it does. So that's the universe as it is now. And cosmology tries to figure out how it got that way. And some of the very early observations I mentioned early in the 20th century were made by Hubble, who looked at galaxies, so these large groups of stars. And what he noticed when he looked at them were that all the galaxies were rushing away, well, from us and also from each other. And he realised then that what causes that is the universe expanding. So it's not like an explosion in the corner of the room that sends everything out in one direction. It's space and everything expanding. So it's a bit like drawing things on the surface of a balloon and blowing up the balloon. Everything gets further away from everything else. And also the further away two things are, the faster they're moving away from each other. That doesn't happen with an explosion in the corner of the room. Sorry. So Hubble realised then that the universe is expanding, everything's getting further apart. And so if you wind time backwards, everything would be getting closer and closer and closer together. And that led to the idea of the Big Bang. So something happened very early on in the universe that caused space to expand. And as things expand, they get cooler. So something happened. Space has been expanding and cooling ever since. And you can actually see the light, the heat that's left over after the Big Bang today. And that's what we call the cosmic microwave background. So that's the stuff that I do my research on. Now this is a picture of it. And you might look at it and think that's probably the most boring picture in all of astronomy. So one thing you'll notice about it is that this radiation, I'm going to say radiation, I mean light, it's called electromagnetic radiation. I keep forgetting, and I call it radiation, but this is what I mean. So this light comes to us from all directions, and that's important. It doesn't just come from our galaxy or other stars or anything like that. So the fact that it does come from everywhere and it's the same everywhere is actually it makes it very interesting. For those of you who are scientists, the spectrum has what's called a black body spectrum. So it has information in this tells us that this radiation came from a time when the stuff in the universe was very close together and the light kept bouncing off it very quickly. And also the fact that it does look so similar everywhere tells us something else that's very interesting. Because if we look at one point of this, I've just circled two random points here, look at one point here and another point, there shouldn't have been enough time in the universe for those 2 points to have been in contact. So light, for any physical thing to affect two places in the universe, there has to be enough time for light or some physical process to travel between the two. But actually there was never enough time for light or information to travel between those points there. They shouldn't be the same temperature. So for them to be the same temperature, the Big Bang Theory said, well, you would have just had to start off with them being the same temperature and I'll keep it the same temperature. But you had to impose it and say it just started out that way. It has no way of explaining it. And cosmologists don't like that. They don't like having to impose what are called initial conditions. So to get around that, came up with a theory called the theory of inflation, which they added on to the Big Bang. What inflation says is that there was a dramatic increase in the size of the universe really early on. So this is, when I say really early on, it's like 10 to the minus 32 of a second, so 0.000, like 31 zeros, 1 of a second. So this is really very shortly after the Big Bang. And the universe expanded hugely. And how that helps is that says, well, these 2 points really weren't as far apart as you thought they were. They were actually quite close together. And inflation just sent them hugely far apart. So the fact that this does look rather boring is actually very interesting for scientists and led to this theory of inflation. So we look at this radiation. So for many of you in the room, this is what a television used to look like. And when you detuned it, you'd see this kind of snowy stuff. And actually a certain percentage of that actually is the cosmic microwave background. It's radiation picked up from the Big Bang. A few percent of that is. Where we're looking actually in the electromagnetic spectrum, let's go back if I have the spectrum there. No, I don't. So what we're actually looking at in the microwave background is light that's not quite optical, so our eyes can't see it, and it's not quite radio, so radio telescopes don't see it. It's somewhere in between the two. The wavelength of most of it is about a millimetre. That's what we're talking about. So that's why we call it microwaves. And of course, when the universe started out, it looked very smooth, but gravity magnifies these kind of things. It helps structure to grow. So if we have a little cluster of atoms, it has more gravity than the area beside it, it'll push more atoms close to itself. So structure grows over time. So a universe that starts out looking very smooth, you know, like the microwave background looks, can actually grow structure and can form things that look very much like what the universe does today. And we can do that with computer simulations and have a look at that. The early stars then that formed were really massive stars, and the bigger a star is, the shorter it lives. Even though it starts off with more fuel, these are kind of live fast, die young stars. The very first generation of stars were huge, probably closer to small galaxies, so they didn't live very long, they died. And the next generation of stars formed after that. And they're the stars we kind of see today. So this is our idea of cosmology now. We have this inflation very early on, which stretched the universe hugely. The light that comes from that early time we see as the microwave background. It takes a while, called the dark ages, but after a while stars start to form, enough matter clumps together, nuclear reactions switch on, and we get stars and we get galaxies. And the universe does keep expanding, this nice kind of big bang, much more gentle expansion than compared to inflation. Now that's what we thought the universe was like till about 1998, and cosmologists did experiments to try and find out how fast it was expanding, because if the universe has a lot of stuff in it, it expands, but then the stuff slows it down and could even contract it again. So we knew it had to be slowing down because that's what gravity does. You know, if I threw something up here, it would slow down, it might stop and come back again if I didn't hit the escape velocity. And when they tried to measure that in 1998, everybody was very surprised to find actually it wasn't slowing down, it was speeding up. It was doing the opposite to gravity. So this is now what we believe the universe is doing. Expanding hugely, then expanding with the Big Bang. Should be slowing down a bit because gravity pulls it in, but actually now it's starting to accelerate. So there's something there that's doing the opposite to gravity, some kind of anti-gravity. We want to try and explain that as well. So these are the kind of questions we want to answer now in cosmology. We want to know how fast the universe is expanding. We want to know how much stuff is in the universe. What will happen to it in the future? That will depend on what kind of stuff is in it. The normal matter that we're used to dealing with will slow the expansion down, but clearly there's something there that will start to speed it up again. To hide the fact we know nothing about it, we call it dark energy. We want to know what the shape of the universe is, and so on. We want to know when the first stars were made, when the first galaxies were made, and things like that. So that's what cosmologists do. And to look at that, one good way is to look at this microwave background. So just a little explanation of where the microwave background comes from. The universe is almost symmetric in many ways. Now, for every particle of matter, so electrons, protons, neutrons, you also have antimatter. So the antiparticle of the electron is the positron. It's the same as the electron, but it has a positive charge. It's its partner. And if you have matter and its antimatter partner, and they collide, they'll annihilate each other and form pure energy. And it's Einstein's equation that tells us how matter gets made into energy. And c is such a big number, the speed of light, that you get a lot of energy from a little amount of mass. And the universe was almost 50-50 matter and antimatter. So the 50% matter and 50% antimatter would annihilate and give us pure energy. Now luckily for us, it's not exactly 50-50. For every about 1 billion antimatter particles, there was 1 billion and 1 matter particle. So most of them annihilated and gave us energy, and a little bit left over to make us and stars and planets and galaxies and everything else. But all this light, energy, we see around us. And that's something like the microwave background. Oh, unfortunately I don't think the picture is coming through on that. So anyway, I can get back to the talk. Yeah. Yeah.
Oh, there it is.
Oh, yeah. No, there was another picture. If it doesn't work, it doesn't matter. There were more pictures. No. Okay, there was a picture behind that.
Which cannot be displayed.
Yeah.
The red box.
Okay, anyway. Sorry about that, I'll give it a go anyway. So, what happened very early on, the universe was very hot. And when the universe is very hot, it's very hard to make stuff like hydrogen and helium and things like that. So what we have when the universe is very, very young and hot is lots of particles, like particularly electrons, that are just floating around. They're not tied up inside atoms. And light, all this stuff that's left after the annihilations, bounces off electrons. So here I had an idea of us being over here, and as we look further and further away from us, we look further back in time. So we look past all the stars and galaxies and things like that. You'd have to use your imagination for this picture here, I'm afraid. But when it gets really far back, the light doesn't travel very far before hitting an electron. And this is exactly what happens in a fog. So you can't see through a fog because the light just gets bounced the whole time. So very early on in the universe, all the light, all the radiation, started hitting off the electrons, didn't travel very far. So we can't make out much from the universe way back then. But what happens is when it cools down, suddenly we get hydrogen being made, and the light doesn't scatter very well off hydrogen. It actually can go straight through that. So all of a sudden, the light travels in straight lines to us now. So we can look further and further away from us, and we're going further and further and further back in time until we kind of hit a wall here. It's called the surface of glass scattering. We can't see behind that, no matter how good our telescope is, because it was foggy. This is the microwave background. This is the light that we see. And if we can make out any information on it, what we're seeing is actually picture the universe right back here, because that's the last time it hit off matter. This actually happened about 380,000 years after the Big Bang, which is not much in terms of cosmology for a 14 billion year old universe. So when we look at the microwave background, we're actually taking a snapshot of the universe as it was 380,000 years after the Big Bang. And scientists soon realised that really it shouldn't look that uniform, because we have stuff around us today. We just saw all the stars and the galaxies, and they must have been there at some level at that point. Maybe very tiny, but we should see something there. So around from the 1960s, 70s onwards, we improved our detectors. First of all, you could see something like this. So you could see that the microwave background is hotter in one place and colder in the other. That's actually just because we're moving through it, and it looks a bit hotter in the direction we're moving through. So nothing to do with the universe there. The bit along the middle is where our galaxy is. So it's very hard to remove that. So you kind of have to ignore any features along here. But we ramp up the sensitivity a bit. And first I suppose it was Cosmogee, but then in the early part of this century, about 2003, an American satellite made this picture of the microwave background, and suddenly you can start to see information on it. And you can see information from Planck. Again, I'm not sure if that's showing all the data there. Some of the slides are missing. But what this is features on the microwave background, hot spots and cold spots, only about 1 part in 100,000, a little bit hotter and a little bit colder. And the microwave background is only 3 Kelvin, that's 3 degrees above absolute zero, about minus 270 degrees. So space is very cold now, it's expanded a lot. So these features are tiny, but they're telling us about the really early universe, matter and stuff, just beginning to clump together to form galaxies. So I just mentioned very briefly, I'm running out of time, some of the experiments that we're involved in Maynooth. We're involved in an experiment called Planck, which is the European Space Agency satellite. So Ireland is a member of the European Space Agency, so we pay a certain amount to that every year. And it went and tried to make maps of the microwave background. Of course, to do that, it's very difficult to do from the Earth, because we're looking for features which are really tiny. So one good place to do it is from a point that's 1.5 million kilometres away from the Earth. So we're well away from the Sun and the Earth, and we can orbit around this point called L2 here. Of course, if anything goes wrong, there's no fixing it like a Hubble telescope. So that Planck went out here, observed for about 2.5 years, made 5 maps of the sky, and made those wonderful pictures I won't show that movie. And from looking at the microwave background, you can tell a lot about the universe, because this had to travel the whole way through the universe to get to us. And this is what we discovered last year, from the Planck measurements. The universe is about 13.8 billion years old. It contains about 5% ordinary matter. So the normal stuff we're used to dealing with is about 5% of everything. We used to think we had a problem with dark matter. There was stuff there that we could see its gravitational effect, but we couldn't actually see it. We called it dark matter. Now we know that that's not our biggest problem. Our biggest problem is dark energy, so that almost 70% of the universe, we've no clue what it is. So microwave background tells us how much of it there is. We still don't know what it is. And that's one big problem facing cosmology. Planck results also throw up a few little funnies I won't go into, but really it agrees extremely well with the Big Bang and the predictions of the Big Bang. Now, one other thing we can do, we want to study the universe, not just the Big Bang, but this theory called inflation. We haven't proved inflation yet. And one way we could do it is by looking at the polarization of the light. So light is a wave, so it's got a direction. So it could be polarized. In this case, I've drawn the green wave moving up and down, the red wave moving across. They've got different polarization. So light can have a direction. And the microwave background, the light from it also has a direction. Now, and pretty much you get almost the same in every direction, almost. by about 1 part in a million or less, you get a slight favour for different directions. You get patterns of directions on the microwave background. And actually, this theory called inflation will predict certain patterns. And that's what the experiment that Aoibhinn mentioned, BICEP, thought they had found, this pattern of polarisation. Planck made a map of the foreground of our own galaxy. Remember, we have to look through our own galaxy to see this. And actually what they saw was that our galaxy is polarised, and what the BICEP experiment saw was not polarisation coming from the universe, but coming from our own galaxy. So we're still looking for this polarisation. Any of the instruments so far have not been sensitive enough to see that. So we're trying to do that. Best place to do it would be from space, but you're not going to get money to build a space mission without knowing exactly what signal you're looking for and how best to do it. So we're trying to figure out how to do it. And one good place to make these kind of measurements is the South Pole, which is very dry. Antarctica is very dry. This kind of radiation doesn't get through water well, so Ireland's obviously not a great place. South Pole, and you get great nights, of course. You get 6 months observing night. So South Pole is a good place. We used to work on an experiment called Quad, which measured some polarisation, but not the particular pattern from inflation. We're now working on an experiment which is going to go to Dome C. So this is a French-Italian, so it's a European station in Antarctica. Oops. My time is definitely up. So anyway, we're trying to design an experiment now. This is some of the research that's ongoing now, is to try and get an experiment there on Dome C. So it's quite far inland, it's very cold. Those places are the coldest places on the planet. It's also up very high. And we're trying to measure now that polarisation on the microwave background. So hopefully soon we'll be in a position to say whether the theory of inflation, like Big Bang, is correct. Well, I'll leave it there.
Super. Thank you so much, Créidhe. I don't know about you guys, but I love hearing anything about astronomy. It's why I originally went into physics, so it's just something I think that lights up everybody, because we can all look at the night sky and we can all imagine, but it's when you get somebody who's actually working in the field and researching in that field that makes it really, really interesting. So I have a couple of questions, but I kind of took over, I think, in the first one. So I'll take the questions from the audience first, and we've got a man with his hand up. So do you mind standing up, and I'll repeat the question for people that may not hear you.
No, just the last I heard, Ireland wasn't a member of CERN. Should we, and what would we gain from it if we did?
Okay, so a very good question, maybe for a particle physicist, but we're a member of ESA, as you said. Should we be a member of CERN?
Yeah. Well, so I can speak from the point of view of ESA, so it's the European Space Agency. So it's a similar kind of intergovernmental, European-wide collaboration. And we say we are members of that, and this is what's funded any of the research, because the science funding agencies now aren't particularly interested in astronomy. So something like CERN would give us this kind of benefit. Also, there's the European Southern Observatory, which is what astronomers want to join, which is the sort of the European group of telescopes, mainly based in places like Chile. And I suppose what it does is it gives us a chance to take part in really the frontiers of science. It gives young people, students, postdoctoral researchers a chance to go to these places and to get experience, and they can, of course, come back. From an industry point of view, it allows industry to bid for contracts. So, I know some of the figures may be better for the astronomy organisations, but even things like building roads and building infrastructure, there's a huge amount of money to be made on that, and you can't bid for it unless you're in there. So, from a point of view of science, I mean, CERN is the best in the world at what it does. There's not an American one that's better. Europe is actually at the forefront. It is the best. So, I mean, I think for a country, I can't understand why you wouldn't want to be part of these organisations, that we can play our part, and unfortunately at the moment we can't really exploit it particularly well. So yeah, obviously I would think so. The relative amount of money isn't necessarily huge. Like for something like the European Space Agency, it's like a cinema ticket each year. And if people will pay that to see Star Trek, you think maybe they'll pay to actually find it in reality. So I mean, I think it's a good use of money, and I think we get a lot of benefits directly to industry, but also I think indirectly.
I think that's a really good point, actually, because it wouldn't cost an awful lot for the country, if you think of the grand scheme, to become a member of CERN. But one thing I think we should all think about, and my colleague here, Professor Shane Bergen from Trinity, it's something that he always brings up, that even though we've got ministers who are in charge of science and research and innovation, there are no politicians who have a scientific degree. And so we can't really expect them to know what we're talking about when we say to them, we want to be a member of CERN, we want to be a member of ESA, we want to be a member of the observatory in the South Pole. So I think it's really incumbent on us as people who are interested in science, people who work in science, that we actually lobby our politicians and really get them to understand why that's important. And if I can hijack your answer as well a little bit, Créidhe, I was lucky enough to be a student in CERN as part of the summer scholarship. But there are only 2 students from Ireland that get to go every year. And in other European countries, it's 30 and 40 that get to go. And the experience that you get working as part of an international research team is phenomenal. And I think more undergrads should get that experience. So I would be definitely lobbying that we become a member of CERN, most definitely. Is there another question? Yes, so we've loads of questions. So I saw your hand up first, so I'll take yours, yeah.
What are next best theories apart from inflation that explain the homogeneity of the Cosmogee disconnected parts of the universe?
So are there other theories better than the inflation that explain that homogeneity?
There are other theories, but I think inflation is definitely the most popular one. It's the most widely supported one. As the measurements get better, we may rule out certain types of inflation, so there'll be people working on different flavours of it and adjusting it. So I suppose inflation is maybe a kind of an overall description of types of theory. And to my knowledge, it's the front runner. But observations like say of this polarisation, which actually be left behind by gravitational waves, so it's a definite prediction of inflation that would send these gravitational waves through space, would leave this imprint behind. So we would like the clincher. So it is the most favoured group of theories. And even if it's right, you still want to find out exactly which one is right, which type is right.
Okay. Thank you. We've got two questions here at the front, so this lady first.
I'm curious, you were talking about how we won't know what the end of the universe will look like until we know what's in it. And I learned various theories in school, but what is the most popular theory at the moment?
So basically, what's going to finish us all off at the end?
It's unfortunately most likely just going to get less and less dense, bigger and bigger and bigger and colder. Already there's not very many stars being made anymore, so the main era of star formation is long gone. The only places left where you get new stars is in the arms of spiral galaxies. So I'm afraid, unfortunately, it's a cold, fairly undramatic ending. Already we've gone from, say, the Big Bang, which is extremely hot, to 3 degrees above absolute zero. So, we're pretty cold as it is, and it's just going to get colder. That's most likely because of this accelerated expansion.
So we're going to end up cold and lonely, so vote yes and 5. And our last question.
I'm just wondering what you think about the multiverse theory, whether there is evidence for the multiverse theory in the cosmic microwave background, the idea there's ripples in it and that's evidence of for multiverse theory. I wonder what you think about that.
So just for the people down the back, the question was, what about the multiverse theory that perhaps, is it that there are different universes?
That they bounce off each other and they cause ripples in the microwave background.
So the universes are bouncing off each other.
Evidence for that,
at the moment there's no observational evidence for it. Now, these inflationary theories, when the universe expands, they're kind of saying what we call our observable universe is actually one tiny bit of something that's much bigger, and we'll only see our one bit. But kind of beside us, there's a whole other universe, and more universes. We don't see any evidence for it, but it's not something that we would have seen by now anyway. So the evidence that we have so far is just agrees with our universe expanding from a very small region. I don't know if you come across quantum theory, so we know the statistics of quantum fluctuations, and this is exactly the statistics that we see in the microwave background. There were people looking for funny shapes, so unusual features in it, and since the Planck results, there's no evidence for unusual features in our. But of course, outside our observable universe, we just can't tell.
So again, we'll continue this conversation at the end of the evening. I want to give a huge round of applause for Créidhe O'Sullivan for the talk on early universe.